sometimes we want to find the relationship between some of the variables that we have, like independent or dependent variables. These cases are very good cases for another class, supervised learning, which is called regressions. Regressions in this example, which is a very simple one, looks at the effect of the mileage of a car to the price of a car and tries to find a linear relationship between the price and mileage. But it could be that there's like a non-linear relationship or polynomial relationship, any other type of relationship that we can exploit, we can imagine, and be categorized as a regression problem. Now, these individuals, as you see, instead of finding what class the points belong to, for example, they belong to image of a person or low-risk clients or an image of a car, there's a trend in the data, or there's some continuity in the variable that we want to basically predict, which basically means that we can find a line which best fits these data points, and that will be the equation of that line will give us the regression that we have. And then we can use the unseen data points, unseen variables, for example, for this new car, which we have their mileage only, but this belongs to the same category, to find, okay, what would be roughly the average price of the car if you want to have a prediction there. Very high level, moving forward, next category, as we discussed, was unsupervised learning. And as I mentioned, one of the biggest parts of unsupervised learning is clustering, which looks into some similarities in the dimensions in the data, in the features in the data, and then tries to tries to cluster those as one group, those data points as one group. Now, thinking about this very high level view of machine learning models that we can build from unsupervised, from supervised classification and regression, build of a model by itself would go. I'll answer your question, 𝗪𝗲𝗽. I'll answer your question. Build of a model by itself needs to basically needs to be followed into different stages. When we want to build a model, we start from the data. We start by understanding the data. We start by finding what are distributions within the data. If it's age, what's this maximum? What's this minimum? Does it make sense? Do we have any, for example, values which are outliers, which don't make sense, which they don't make sense to the business? All of these information, we have to go through it and then find information, make sure that our data is ready. And then it goes all the way to build of the training data set, and then build of a model, and then validating the model. All of these small stages that we have to take is together called a machine learning pipeline. Now, let me pause here. Let me answer 𝗪𝗲𝗽's question. And if you have any other questions, please feel free to ask. Deep learning has nothing to do with supervised and unsupervised learning. Deep learning is a part of a neural network learning, which can be both supervised or unsupervised. Thinking about, for example, the classification. In the classification, when we want to classify, let's go back to the image problem, which I mentioned, classify images of the humans versus non-human images. The techniques that we can use could be very different. The techniques could be using different algorithms and different procedures to implement that. One of these procedures is deep learning. Deep learning is basically inspired from how human brain works, and creates basically series of layers of neurons, artificial neurons, and then which each series and each of these layers try to extract some information about the data. If it's image, for example, the first layer might learn the, if it's a human face, it could be learning the shape of the eye, or the curvatures around the nose, or if the curvatures around the head. So all of these feature extraction will happen, and will happen at different layers. So it's a totally different category of learning, and it's very, very well known and being used very frequently right now, because that we have much more computational capabilities at the moment. But deep learning can be applied to unsupervised learning or supervised learning. Okay, let me continue. Now, going back to our discussion and then the machine learning pipelines, we start from gathering the data, understanding the data. What data do we have? And then validating, and then go through different phases. I read the phases first. Data validation. Validation of data, we'll go through it in a little deeper, would be understanding the data and making sure that the data is right. Then it will be data pre-processing. Data pre-processing, for example, I will go to each of these stages, basically in next slides, would be understanding and knowing how to deal with some issues in the data. For example, if we are missing some values for some of our data points. Consider we have our clients or customers data, and some of this data for some of these clients or customers, we don't have their age basically being populated, or we don't have their income being populated. How do we deal with such scenarios there? And then, do we want to create new features and new data by combining some of these variables that we have in the data? That is another thing that we can do in data pre-processing. Then we go and train a model, and then we make sure that the model we train uses the best possible parameters, which basically means that we're upscaling model's performance to the best possible value which can be. And then we go and analyze the model, verify and test the model, and make sure that the model that we have built not only works for this data that we have, but when we are using the data which model hasn't seen and model hasn't been built on, still it performs very well. The rest of it would be on making sure that the model still is valid. Basically, we do proper documentation on model versioning. We go and then deploy, basically productionize the model, and then know that, okay, till what time, and applying some measures, we monitor the model's performance and know till what time we can use this model. When will be the time that this model is useless? It needs to be rebuilt from the scratch or retrained from the scratch. All of these are different stages in machine learning pipeline. Now, thinking about the data would be the beginning of the problems. The expectation is always that, okay, I want to build a model. I've been tasked from my manager or from the business line or whatever to build a model. I'll need one data source, and then the time which I need to get access to this data and then start building would be very fast. But the reality is that this is not only going to be one data source, there will be multiple data tables and then information that needs to be extracted from different resources. Some of these resources could be external, some might be in the cloud, some might be in different servers, which needs separate pipelines to be built for them. And then the data access and then acquiring access to data could be very challenging too, because the format of data might be different. So these are the problems that we will face basically in the very, very first phase, and to understand and then to make sure that we have access to the data. We have to also think about how we can use the data, how we can benefit from the data. As I mentioned, the format of data could be very much different. You can have a data very simple as an Excel file, or a data which is in a DB2 server, or as you can see in this example here, the data could be in a Parquet format. And you have to make sure that you have created a good data engineering pipelines where they can extract and then read all of these data from these various sources and put them together and create the maybe one data which helps you to build your model, to create your model. This basically shows some tech stack which basically will help in the building of such pipelines, building of such infrastructure to read data from the different resources. All of them are open sources, which open source basically data codes or open source tools which could be leveraged, and you're very welcome to start playing around with those if you're not familiar with some of these. Basically, if you're familiar with some programming tools, you have probably used, especially Python, you have probably used Jupyter Notebook, but I don't want to go into very much details here. Maybe it will be like boring for the audience, but let me stress on Apache Spark if you're a Python programmer again, or a Java programmer, you can use Spark version of, let's say, Python PySpark, Python version of Spark, or the Java version of Spark, or if you know R, there's an R version as well. And that enhances a lot of things, because with that framework, which you can build with Apache Spark, you can access different and various different data sources. And as I mentioned, you can read all these different types of data from different servers and then create the basis of your basis data for your modeling. I'll continue. Before we get to data validation, are there any questions? Okay, we'll continue. So data validation, now consider we have access to the data, we are able to read the data. Now we have to understand the data. That is one of the most important phases in building a model in machine learning. We have to understand what are different, so consider Excel file or of a data, we have whatever CSV file. Each column would be a variable or a feature within the data. Consider, for example, if there's a data related to car, one column could be car's mileage, for example. That could be one of the features there, or the number of I don't know, the maximum speed it has, or the weight of a car. All of these could be different features or variables in our data. The data is related to car, but we need to understand those by doing a series of statistical tests. This statistical test could be very simple in looking to, okay, what is the mean value? What is the maximum value? What is the minimum value? What's the standard deviation? Looking to the variability of these features there, looking to correlation between these features, and then understanding, oh, how these features are basically changing with each other. This is very, very important. And then on top of that, you can use some visualization tools and looking to, for example, histograms within the data, and then try to basically understand the distributions better, distribution of each feature. I give you an example. If you're building a model, for example, going back to our credit scoring, and one of the features is age, then probably you want to think about, okay, if I have an age as a negative value, does that make sense? For sure it doesn't. Or if what's the highest age which I want to include in the model that I want to build? Or what's the minimum value there? Would it be 18? Would it be 20? Would it be 10? That comes from by basically working with the business as well. Now, going back to our example here, in data validation and exploratory data analysis, as I mentioned, we try to understand the features which are within the data, or variables which are within the data, and then we can use visualizations there too. One of the most, for Python, again, programmers, but one of the most well-known packages that you can use is 𝗪𝗲𝗨. If you're all programmers, you probably are using it already. And there are already automated tools that you can use, like pandas profiling or 𝗏𝗏𝗡, which I've basically listed here as well. That enhances the work very much. But the main idea, going back again, is to understanding the variability, the correlation, the basic statistics of all of these features within the data. After that, we go to data processing. Now I understand the features. I understand, okay, if that was the age, I know that, okay, this is the distribution. This mean value is around, for example, 35. I have removed the rows which contain the ages which are not making any sense, the negative value or values which are too high, or I've applied some treatments there. When it comes to the pre-processing, I continue this work by seeing, okay, if there is some value in the data is missing, or I need to apply any diagnostic to my data prior to build off the model, what are those treatments and diagnoses which I'm going to apply? Looking back at some values here, for example, you see for this table, the value 1 has there's a missing value for value 1. And then you can see that the date of birth here, maybe it's something that I don't want to use in my data. Another thing that you might think would be that even the age might be, I make some decisions of, do I want to use the actual age value in there, or do I want to use the category of age? Say, okay, from the age of 18 to 36, from 37 to 45 and onwards, basically bucket that and create beans around it. All of these, as you can see, is basically part of the data pre-processing. And the richer that is, the better chances are that you can create a better model, a good model for when you're training the model at the next step. As you can see here, there are techniques that you can impute the missing values. There are techniques that you can replace the missing values by finding what is the mean value, what is the common value in the same group of people. Thinking about, for example, say computer programmers. If you don't have a value for their income, of maybe 1 or 2 people, maybe using their the job, which is basically the computer programmers, and the level of experience, if that is in data, you can replace that by a median value or by an average value, which basically there, and that will help with some imputation of some missing value and will basically enrich your data. These all techniques can be applied in the data processing, pre-processing. In terms of, I saw that there are some presentations on text programming, on NLP, basically on natural language programming. So let me just talk about that a little too. In these cases, when you're dealing with actual text, you can work on all the work that you do on tokenization, on POS tagging, lemmatization, stemming, bagging. All of these will be considered as proper pre-processing steps. One of the most important parts in the data pre-processing is feature engineering. Feature engineering will greatly help the model build, because with feature engineering, you can create from one feature, you can create series of other features which will help and boost up your model performance. Consider, for example, you have you're looking into what should I say, credit score of a customer over last 6 months or 6, 7, 8 months. So you have 8 data points for this customer. What you can do is you can take an average value, as long as you can include all the values, that what was the mean value, what was the maximum value, what's the standard deviation. All of these features basically will help you to increase the chances of building a more robust model. featuring, there are some tools that you can use and automate the feature engineering, but it's one of the most time-consuming, but was one of the most important phases of the machine learning and model build, which will take away a lot of time from the data scientists. And then a lot of times when the model is not performing well, one of the key things which will be taken into account is, would that be increasing the features, revising the features which are there, and then seeing that how we can enhance the feature space that we have by adding more features or making it more efficient. After that, now we reach to a point that we want to build a model. At this point, there will be, we have to choose what type of algorithm we want to use. Like Hardeep said, do you want to go and use deep learning? Do we have enough data to, for example, do we have enough data to back that up? Or shall we use a simplified algorithm? How much time do we have? How much resources do we have in terms of the computation? Are we going to use GPUs? Are we going to train the model in the cloud or on our laptops or personal computers? So all of that information will matter on deciding what type of algorithm do we use. As you can see here, this example data set says that, okay, you want to predict whether somebody will default on a loan or not. And we have this data which says that actual people who have defaulted on the loan, and these are the different, so this is the ID, so we'll remove that. And then there are actually three different features that are associated with this data. And this is what we want to predict. This is the default column here is what we want the model to learn. And we have another unseen data which we don't know the result, or we don't know the outcome of it, or we know but model shouldn't know the outcome of it, so we can verify model performance with that outcome. In this case, or cases like this, what we have to do at the beginning would be to divide our data into some training data, which we use to train the model, to build and develop the model, and another set of data to test the model. Training data, in this case, oh, can I go back? Training data in this case would be something like this. And then testing the data can be this row that we can see here. The rule of thumb is usually around like 70% of the data has been chosen, selected randomly or based on some techniques to serve as the training data, and then we use the remaining 30% to validate our model, to know how well the model is being trained. After this, we have to choose what algorithm we want to use or what type of machine learning model we want to build, which I don't want to go into details, but it could be regressions, as we discussed a little. It will be neural networks, which could be the basis of the deep learning, or it could be a tree-based algorithms, if you're familiar with, or it could be a very simple decision tree, or series of trees together, which are called random forest, or using more advanced techniques like gradient boosting, which is called XGBoost, by the way. Looking at a very simple example, which is a decision tree, you can know the tree-based algorithms, what they learn about this data is set of these rules, which basically can be applied to the data and explain basically why a decision is being made. Now, if I use this test data and I want to use this tree, the learned model from this data, I can simply just use these rules which have been learned by the model. Saying, okay, income is, for example, 100K. Okay, what category does it fall to? And then the loan that is being requested is $2,000. What is the loan to income ratio? Okay, this is the feature basically which is created from these two features. and that is being used to see if a person will default or will not be default. So this simple tree algorithm will help me to explain the rules and explain why a model has come to a decision. Now, considering I've built the model and I've tested the model and the model is in a very good performance, I have to assess it. When I assess the model with the test set which I have, with the test set which I put aside, I'll get to some regions that I have to, which help me to identify model performance. Those regions is they serve as they look like a matrix, which is called confusion matrix. And if you look into, so let's just ignore how they're calculated, but let's look into these 4 blocks which are here. The green ones are the ones that model basically does a good job and then classifies them and predicts them correctly. And so true positive is, for example, if the person has defaulted and the model also predicts, okay, the person will default. True negative is, again, if an actual person has not defaulted and model has done a good job in predicting that as well. Then we have false positives and false negatives. If actual person is not defaulted, but model by mistake predicts it as default, and the other way around. If the actual model has defaulted, a model by mistake says it's not default. Using these two together, so the number of cases basically which are true positive, there are a number of cases which are true negative, and then adding these two together and then dividing by the total number of cases that we have will give us a metric called accuracy. So when we say a model, I build a model and this model is 95% accurate, that is the accuracy we're talking about. By adding true positives and true negatives together and dividing by the total number of cases that we have. We have other factors there too, like precision, recall, and F1 score, which are way better than using the accuracy itself. But if you have questions, I'll be happy to answer. But or if you want, at the end of this, I can send some links for you to go through them or to try to basically understand them. But just giving you some examples that accuracy is not always a very good measure, because the distribution of let's say, for example, default and non-default, it could be that the distribution of this class of default and non-default could be very rare and very skewed to one of these cases, for example, on non-default, which is basically means that there could be, for example, 10,000, for each 10,000 cases of non-default, it could be only 1 cases of defaulting. And what is important for us is finding that single person who wants to default, because our company will lose money if that person defaults and we don't predict that correctly. But if we add the 10,000 true negatives and then even misclassify this one single person there, for sure our accuracy will be more than 99%, but the model will not be useful at all. So that's why the measures like precision, recall, and F1 score, which is the average harmonic average of these two, will help in identifying and addressing these type of issues. Any questions? Now, after I build my model, build a decision tree, I validate it through the test set which I put aside, and then I'm seeing, okay, the model is working okay, the performance on F1 score or any other measures that I've extracted from a confusion matrix is basically good enough. What I'll do is I have to put in a model basically in a format in a in a place where it could be used. It could be used. By that I mean that it could be leveraged by new data. When the new data is being generated, the model could be used to score that. If I have new data of my loans and then this information about the loans for this new month which I'm getting, I should be able to load the model. I should be able to feed the model with these new data and get the outcome values and then send it back to whoever is asking for it or use it for my own purpose. This, in general, is called deploying the model. Now, deploying could be also happening in various different ways. Could be, if it's like a very small, like, for example, a company, it could be your own laptop, your own server, your own machine there, or it could be in the cloud, in Google Cloud, in Amazon, or it could be in like companies' infrastructure servers that they have for these purposes. But the main parts which is important in deploying a model is how we load the model and then make sure that the new data could be scored. By scoring, meaning that the new predicted values can be generated for this model, and then till what time, till what date, what month we can use this model. Because what happens is patterns change, I mean the data will change. Data over time will go under a lot of changes. And these changes will have impact in great impact in model prediction. That is called model monitoring. So with model monitoring, we can have some thresholds, or we can set some targets and say, okay, as long as the performance of model, for example, is in this region, we accept this. Or as long as this as long as the distributions in the data which is feeding the model is aligned with what the data that we use to train the model, we can hard code all of those, and then we feed this new set of data that we have to the model which is running in the backend. And this new set of data will generate a new set of scores, which we can basically save it in a table, save it in a new place, and then feed it to our visualization tools, or feed it to our whatever, send it to our business, or send it use it for start consuming it. I promised so not to talk about this, but in general, this shows the real time and then how the streaming will work, but it will be much faster. But in terms of the infrastructure, it needs for sure, it needs a better architecture and stronger resources to make sure that it is the predictions can happen online. Now, it could be created through web servers or web applications. If you're doing API programming, you can create, if you know about API programming or have used API programming in the past, you create a REST API, then you make a call to the entry point that you have created there and get the response back as the model scores. In the streaming way of doing it, you need a pipe, basically. You need a pipe there which contains the data points, and then you can use a tool which basically reads from this pipe and then reads the data from this pipe and then feeds it to the model. This pipe is called a broker. In like computer science architecture, you probably have heard about it. A message broker in GCP or GCP, some Google Cloud, if you're using, there's pops up which is available. You can use, which basically you can create to this pipe of data, and then one of the tools that is very good in reading these data points from this pipe, from this container, is the Spark streaming. which basically, again, needs a very strong back end to make sure that everything works near real time or with a very small delay. This is how things will be in reality, actually. You will have how an automated pipeline for batch prediction in reality will work. You can have different data sources, using Spark, you can read the data, load the model, apply basically the data to the model, and then create the scores, create the predictions of the model, and save them in some databases on some places that you can leverage later. Now, let me briefly talk about model monitoring as well. And then maybe this is one last slide, or just maybe one more is left. Model monitoring, with model monitoring, as I mentioned, when we look into the drift, the changes in the data, and then the changes in the prediction of the model, if we are saying default and non-default, if for every month the model's distribution is that, okay, model's prediction distribution is that from like every 1,000 cases, there are only 1 cases of default, and that is consistent, all of a sudden we'll see a big change. Either there is a change of pattern in the data which model is not aware of, or the way the data is being basically created has changed. And then again, model cannot do a good job of prediction. So in both these cases, we need to have some threshold values of these distributions that we have, either on the data drift or model output drift, which is called concept drift, and then use that to validate model performance every time a prediction is being made. As long as that prediction is within our accepted region, or within our or above the performance threshold that we want, we can continue basically using the model. But if it is below the performance threshold, and then we see that there's the work basically has been done in a way that models is obsolete and cannot be used, we have to go back and rebuild everything from the scratch, basically retrain the model, starting from going back to the feature engineering and all the way steps through the model build. Model monitoring is one of the most important phases in the deployment pipelines, and in the deployment pipelines. So the last step in this machine learning pipeline is that making sure the data science or AI solution that we have applied to a business problem is aligned basically with what business wants and is in the direction that is generating value for that business, which is resulted from a good collaboration with the business which we are working with. Either it's the sales department, marketing department, if it's a bank, it's in it like Google sales. So whatever it is, there should be a purpose, business purpose and business problem that we want to solve. And that would lead to generating or training a new model. And this figure, which I showed at the beginning on machine learning pipelines, as you can see, it can go back to getting the feedback from the results and performance and go back to the starting block, because it will continuously, there's no model which is sustainable for like indefinite months or definite time. There will be continuous work of enriching the data, adding new data, start validating, pre-processing, training a new version of the model, and then going back all the way to the deploying it, and then get the feedback from the business. Now, this brings me to the end of the presentation. Let me pause, and if there are any questions here, I'll be happy to answer.